So for our next part of our presentation, we're going to talk about the idea of black holes. If we're going to talk about physics, why not black holes? Because they are insanely cool. So you've probably heard about them in a lot of science fiction, you've seen them in a lot of movies, but do you ever wondered really what a black hole is? No one really gives a good explanation. So we're going to go to what NASA says. According to NASA, basically what a black hole is a very small area with a lot of mass. And for the sake of argument, let's say that this is the size of New York City. Well, if this is the size of New York City, then this has a mass of about roughly 10 different suns. So as you can imagine, we have a lot of mass packed into a very, very small, scummy area of the Earth. Also, black holes are so strong that not even light or electromagnetic fields can get out of it. So as labeled, it's a black hole because you can't even see light out of it. So you might be wondering, how exactly can we detect these in space if you can't see light, you can't see X-ray, and you can't see electromagnetic fields or static? Well, we don't really actually have a full way of seeing it in space per se. However, what we do know about black holes is that they affect the area around it. So when we see a large body of matter around it, around that area that seems to be like shifting or changing in mass, we usually have a good enough evidence to say, yes, this must be a black hole. So another thing about black holes that has also been a very big debate is how it affects time. According to what we know about physics, we know that the stronger a gravitational field is, the slower time is. So a lot of theories and debates have been projected on what do black holes do? They freeze time altogether? Are they even related? Well, we're going to look at some fun facts about black holes and see what actually happens. So we know at the core of a black hole, a gravitational pull is equal to infinity, and this means that time completely stops. But what happens to the objects that are trapped inside of a black hole? Well, according to Einstein's theory of special relativity, speed is indirectly proportional to time. So if you have speed going this way, time is this way. Makes sense. But this means that the slower the flow of time in an object, the faster its speed. Thus, when an object is trapped in a black hole where time is stopped, then its speed should be equal to infinity or faster than the speed of light. Some scientific theories claim that objects absorbed in black holes are either teleported to a different space-time in the universe or they travel back and forth in time. So now that you kind of have an idea of what a black hole is, we're going to look at the force diagram of what a black hole would look like. So you're probably thinking, well, it has a lot of gravity. What exactly could there be for an equal or opposite reaction? Because according to Newton's laws of physics, we see that there should be some kind of very strong value as we have a very strong gravity. So we're going to have an incredibly huge arrow because, as stated before, the gravity of a black hole is so strong that not even light can escape it. So as I said before, while we do think that according to Newton's physics, there should be something that's going to have an equal or opposite reaction to gravity, so far according to current theories, we actually don't really know how black holes work still. We believe that there might be something, but we also know that black holes defy almost all types of physics. So to demonstrate this, I'm going to show you a quick video of what it shows to be light trying to escape a black hole. So for this part, what we're going to do is I'm going to represent light. The hill is going to represent gravity of the black hole. Let's see, if I can make it up to the hill, that means that light can escape, but probably not, because let's face it, it's a hill. So if I can't make it, that's just going to show how strong gravity is in a black hole. Okay, let's go. Okay, I couldn't make it out. That's because to show how strong gravity is. And if you look at it from a force diagram, that's about roughly how big the arrow would be compared to anything else. If there are any other forces acting within a black hole, they will roughly about be this big compared to what I just did. So they're pretty minuscule. And that's black holes.